This approach is called the excursion set approach. The logic for it was laid out in 1991 in a very nice paper by Bond et al. The same Bond who was doing the ellipsoidal collapse models that I just referenced, but we didn't actually do ellipsoidal collapse. Yeah, so, okay, so what we are going to do is we're going to use this approach. I'll describe the approach as we go through to first predict the abundance of halos, the abundance of structures, the mass function of structures, okay? And a byproduct of this is going to be that along with knowing how many massive halos you have and how many low mass halos you have at any given time, so the mass function and how it evolves with time, it will turn out that part and parcel of this description is the spatial distribution of the halos at any given time. And so it's a much more powerful thing than you would initially have thought, okay? And so I will set up both arguments. We'll do this first and then move on to this. Let me do the full screen. Okay, and remember the entire logic of this approach is following from the fact that structure formation is pretty local. Nothing has moved very far, yeah? So that's a plot we've seen a few times. This was the movie we just watched. Okay, and the reminder is the first thing we want to do is we want to know clusters because we can do cosmology with cluster counts. Okay, and so this was a slide that we saw on the first day. So it's just a reminder that that's why we're doing this. And we're aiming for a prediction of the curve that is going through the data. Okay. Okay. All right. So what's one thing that we could do? So this is the final time in the simulation, redshift 0. There are, all these yellow dots are things that would be halos. And so we're trying to predict, how many big guys and how many of the smaller guys there should be. Okay, that's our goal. And we know that the things are 200 times the background density. And so that means that that one approach could be you just pick a position in space, and to illustrate, I'll pick this special one, okay? And I can ask, what is the mass inside this sphere, right? Is it 200 times the background density? If it's above, I will go to a bigger scale. I'll go to a bigger scale until I hit 200. And then I'll say, okay, these are the particles that make this object, and the rest don't. But now let me describe the same procedure the other way around, okay? The other way around, I mean the following. The universe is homogeneous and isotropic. And so supposing I pick this position in space, and I smooth with a very huge filter and ask how much mass. Mass divided by volume is some density, right? And I ask, am I 200 times background density? And the answer is obviously no, because the universe is homogeneous, okay? So I shrink. I check again. I shrink. I check again. And I keep shrinking until I reach 200. Until I reach a volume in which the mass is giving me the 200. And I say, that's my object. Okay? So I'm doing the same procedure, but instead of starting with small spheres and growing them out, I'm starting with big spheres and shrinking the size of the sphere until the size is 200 times the background density. And the reason for thinking that way is that, here, a small sphere will be 500 times the background density, 1,000 times the background density, okay? And we have this prejudice, but a good prejudice, from spherical collapse that if a larger region is 200 times background density, then everything inside it is also overdense and has collapsed, right? And so we want the largest sphere that is 200 times the background density, okay? And so instead of starting small and going big, we're starting big and shrinking till the first scale we get, which is 200, and we say, that's it. So we found the scale.
Doing this around a point, or we are doing it everywhere?
So we will do this around here, around here, around here, so we will do it everywhere. Okay, so that means associated with each point in space is something that is going up and down that tells me the density centered on that position as a function of the smoothing scale.
Then we'll also have overlaps.
So
We will also have
exclude the
overlaps.
particles once you find a halo.
Okay, so we're going there, yeah, we're going there, all right? But so the first idea is that you almost have a random walk associated with each position in space, and this random walk is telling you what is the density around that position as you change the smoothing scale, okay? So that's the kind of thing, yeah? So associated with each of these steps is a density, is a walk.
Actually, the 200 mark, you say this is the realized halo.
Yeah,
But then it will be having some overlap with the nearby halo.
that's right.
So how do we distinguish two?
So we'll come to that. So let me set up the logic first. And so the idea is there is I will call that a detail that we have to worry about. So we'll first do the basic structure of the calculation, then we'll worry about the details of getting it exactly right. Okay, so this is all well and good. This is a procedure that we can do in the nonlinear field, but our goal was to predict the cluster abundances not from the nonlinear field, but from the initial conditions, from the CMB. No, I want to be just given a power spectrum, and I want to know now what are the objects that are going to form. What is the mass function of objects? And so what I really want is to play this same game, but in the initial fluctuation field. That means I want to start with the field, this one. But then I want to play the same game, and now instead of finding when I'm 200 times the background density, I'm looking for when the density is 1.686, because this is the linear field. Yeah? Yeah.
So the density is not uniform in all the directions. So like you have plotted those concentric circles. So,
But the object itself is triaxial. That's what you mean?
no, I'm saying the background density itself is not very spheric like.
Oh, because it was fed by filaments and stuff like that. That's right.
You are saying that 200 times the critical density. So that means the critical density.
200 times
Background.
Oh, background, yeah.
So even the background density is not same in all the directions.
Oh, no. So the background density you should define as in the whole simulation, how many, what's the mass? Divide by the volume of the whole simulation. That is the background. I don't mean the local background. I really mean omega. Yeah? So it's the.
Linear, we consider 200 is the critical density.
Okay.
We reach around like 500 modules.
Okay. All right. So yesterday when we did the analysis, then we did it all for Einstein de Sitter. And that number we derived 18 pi squared, which is 178, which I'm loosely calling 200. This 200 is 200 rho critical and 200 rho background, because in Einstein de Sitter, critical and background are the same. Okay? When we do lambda CDM, critical and background are not the same. Now we have a decision. We have to decide, do we do 200 background or 200 critical? So we can go through the whole spherical collapse argument. And what you find when you do that is that now you'll get a number for when it virializes. And that number is, because the logic is all the same, it's just technically more painful, is for lambda CDM 0.3, 0.7. That number is 340 times the background density. Okay? So it's always of order 200. Okay? But so 340 background is, omega is 0.3. So it's of order 100, 120 critical. Yeah? Okay. But so when I say 200, I just mean loosely there's some number. Okay? And in fact, that number matters a fair amount at late times. 200 is not the same as 350. But in the linear field, the number 1.686, that number is basically independent of cosmology. Okay? And so because now we're doing this in the initial field, this number is 1.686. We can apply the same rule for all cosmologies. Okay? And we're going to do this thing, right? We're going to just find what is the biggest sphere that is 1.686. Okay. Okay? So now I'm going to make a plot in the plane of what was the smoothing scale and what was the density. Okay? And I'm going to do it in a funny way. The large smoothing scale is going to be here, and the small smoothing scale is going to be here. And the reason for doing that is that I know for sure on large smoothing scales, the density is 0 because the universe is homogeneous. Okay? I don't know what the density will be in a small smoothing scale. So then I will have some curve that shows me the density as a function of the smoothing scale. Yeah? This density, it has to cross 1.686. Okay? So that's the thing as a function of smoothing scale. Yeah? And there it hit the barrier 1.686. Over here I have something that I called high Z. Okay? Because if I want the barrier, this number 1.686, that's the height it has to be if it is to collapse today. If it is to collapse at redshift 1, then it should be 1.686 times 1 plus Z. The growth factor is A. That should be 2. So 1.686 times 2. Okay? So that means in this picture, the barrier for something today is here, for something in the past is here, for something far in the past is even higher up. If I want a fixed time, then I have to just cross the barrier for that time. Yeah? Okay? Of course, okay. So the barrier, you know, for some high time is up here and for some low time is down here. The walk, after it crosses the barrier, it's true I can look at what is the density on a smaller scale, but it's irrelevant, right? Because if the big scale was 1.686, it means the whole thing will have collapsed. And so whatever was inside, that will be the substructure that is a bit weird. I don't care. It's all squished now in a smaller volume. Okay? So that means that we have a problem, which is kind of a well-known problem in stochastic processes, right? We have a random walk that is crossing a threshold, and we want to know the first time at which it crosses. Okay. Okay. Now, what we will do soon is try to estimate, what fraction of walks first cross the barrier on this scale, or what fraction of walks first cross the barrier on this scale. And that will be telling me something about the number of objects of a big mass. Big mass means big smoothing scale, and the other means small smoothing scale. Small mass is small smoothing scale. Yeah?
So how do we know exactly that it has to be a random walk?
So for some people, random walk is a very technical thing where the steps are uncorrelated and all of that. Okay. Right now, it's just a picture that I've drawn that shows the density. Okay, and I'm using the word random walk just to say it's going up and down. But for a Gaussian random field, so remember, I took some care to set up what happens when you smooth a density field. And in Fourier space, the smoothing is simple. You're taking the k modes and you're multiplying by a weighting function. If the weighting function is sharp in Fourier space, so it has some weird oscillations in real space. If it's sharp in Fourier space, then this is a smoothing window that will let in one k mode at a time. No? As I make the smoothing window bigger, I get one k mode, one k mode, one k mode. But in a Gaussian field, the k modes are independent. And so if this is my smoothing filter, then the steps in the walk are independent steps, right? Because I let an independent k mode at a time, and so this is really a walk that is really random in the stochastic process sense.
So for one type of filter, this is actually a random walk.
This is actually so let me say it more carefully. It is a random walk with uncorrelated steps. Okay? And this is for what is called a sharp K filter because it's sharp in Fourier space.
And plus, we also have that the amplitudes in the K space are actually Gaussian.
Correct. Yeah.
That's why we have a random walk.
That's right. Yeah. Okay. And so, yes.
I don't understand why you're doing for the first crossing, it's going down.
Because, so if I was to draw a picture of what this means, let's draw a picture. Okay. So I'm looking at the density in successive shells, okay? So the one that crossed the barrier, suppose we crossed the barrier on this scale. Okay? So that says, the spherical collapse model says this whole thing is going to shrink. The spherical collapse model does not care if the reason this is overdense, 1.686, is because all the mass is here and there is nothing in between, or the mass is completely smooth here. Yeah? Either way, it's going to collapse. Okay? And so the walk that steps down and goes back up is like this, no? Is that I was 1.686, then I was a bunch of underdense, and then it was dense again in the middle. So that will eventually climb up, right? But this internal structure doesn't matter so long. It's like Birkhoff's theorem, no? That if this circle is if the sphere is dense enough, it doesn't matter what is outside. It shrinks, and similarly, the internal structure is irrelevant. It's going to shrink. Yeah? So that's why. Okay? All right, so very soon we're going to make a calculation of what is the mass function at one time.
Choosing your center randomly because you are assuming statistical harmony isotopy.
Right, so I'm centering on random positions, which is why sometimes the walk will cross on one scale, sometimes the walk will cross on another scale. Yeah?
If they are large inhomogeneities, then you may be careful about choosing the centers, right? If you are like choosing them properly, then it's like it is like crossing this barrier around some center, but not around the near center.
Okay, so we'll come back to that. Okay, so again, this is a. I will call it a detail, but it's an important detail, okay? And so we'll come back, all right. So statistics of the walk, they are truly random steps, random increments, if we use sharp case smoothing. If we use the one which is sharp in real space, which is the physical one for which we did the spherical collapse calculation, that guy, in Fourier space is the steps, it has funny oscillations in Fourier space, and in real space, that means, this kind of walk, the steps are correlated. So the calculation that was done in the 90s was for the uncorrelated steps, okay? The calculation I'll be describing is how to handle correlated steps, okay? So to do the more realistic thing. Before we do that calculation, I want you to see a little bit the framework of why this is such a nice approach. Okay, so I had a barrier that dropped. Yeah, so go back. So I have this barrier that is dropping. This barrier that is decreasing with time is supposed to say, the barrier when it's high, that's telling me something collapsed at high redshift. When the barrier is lower, that's the necessary condition for lower redshift. And so when I did this, then this is saying, this walk, it crossed the high barrier over here. Then it crossed, the barrier drops. Then it crosses the barrier here. Then the barrier drops. It's crossing. Then it drops to here. Then drops to here as the barrier drops lower and lower. Yeah? So that means that I can read off, because everywhere it crosses, there's a smoothing scale, and that smoothing scale contains a mass. And in the initial conditions, the smoothing scale is the mass, because the fluctuations are, so the mass is background density times volume times 1 plus delta, but delta is 10 to the minus 5. Right? The reason this number is 1.686 is we take this one times the growth factor. And that's why we're getting order unity rather than 10 to the minus 5, right? But this axis is the mass, and the mass is the fluctuation is 10 to the minus 5, so I don't have to count it. I don't have to put the linear theory 1 plus delta. I have to just put 1 plus delta in the initial conditions. Okay.
But as you evolve through the redshifts, wouldn't your density profile also change?
Okay, so the actual object, yes. But right now, we're just trying to identify the patch and the initial conditions. So we're playing a game, right? We're saying, if I was to run a simulation, this whole patch will collapse. But I don't have to account for its collapse to say what will happen on some larger scale, when it will subsequently collapse because the rearrangement of the mass inside is irrelevant. So, yeah. So that's the game we're playing. So we're doing everything just in the initial field. If you're worried about this 1.686 there and 10 to the minus 5 here, then simply think, okay, this number is 1.686 divided by the growth factor 10 to the minus 5, so this is a small number, and we just do everything with small things, that's fine. Okay. Then the condition for collapse is not 1.686, but 1.686 divided by the growth factor for that time, and that's it. So it's a small number. Okay, so the barrier is something that is going to collapse, to drop downwards like this with time. And the intersection of one of these curves with the barrier is telling me what was the mass at some early time, then that mass grew, and then the walk first crosses here. So this represents that the mass jumped in value from here to this value, because there was a merger. And so this object collided with something that was maybe more massive, so its mass jumped a lot. And then this object continued to gradually grow mass, and then it jumped a lot. Okay? And so these are major mergers. This is smooth accretion. Okay? And this is the language that observers use to describe clusters, or you would use to describe what you saw in a simulation, right? If you watched an object change, grow and accrete its mass, you would use this language. And so this is built into here. Okay? Now let's think about what we're plotting on the axes. So, yeah.
So this yellow evolution is basically as the barrier is moving.
As the barrier shrinks, barrier changes height with time. So you can think of this in two ways. Okay? One way to think of it is the barrier is 1.686, and 1.686 represents the linear theory value, which means I have to take the initial conditions and multiply by the linear theory value for each redshift. Okay, so that in that picture, the 1.686 is sitting here, always, and at an early time, when the growth factor is small, all my walks, they are 10 to the minus 5. So those 10 to the minus 5, they're not hitting anything. Or they will, but at very small masses. Okay? Then I would take the walk and I would multiply it by the growth factor. Okay? And so now it's whatever it was, 10 times what it was, 20 times what it was, 30 times what it was. And the barrier is always sitting at 1.686, and that means that the walk will now cross at earlier and earlier, right? Because I'm just taking the same curve and I'm multiplying its height, right? And so that means if the barrier is always fixed and I'm growing this curve, I will start hitting it as the amplitude of the curve increases by a growth factor. I will start hitting it at earlier, so bigger and bigger smoothing scales, and so bigger and bigger masses. So this is entirely equivalent to drawing a walk with one height and just scaling the height of the barrier by the same growth factor. And so that's the way I've done it here, to not change the height of this, but to simply scale the height of the barrier. Okay?
So the height of the barrier is like a clock.
Exactly.
And you're moving it downward to show the evolution of time. And its intersection with that curve, the walk, is telling you how the mass is accreting or changing.
That's correct. That's correct. Yeah. So this lets you visualize that. If I was changing the height of this thing for the different times, then it would be harder to see this. Okay. There is a nice connection, though, to what happens with modified gravity. Because with modified gravity, even the linear theory growth factor depends on k. Okay? And so suppose
The barrier won't be flat.
right, so now the barrier will be some weird thing because, of course, first step is you have to solve what is spherical collapse so that you know what the barrier is in the first place. But the second thing is going to be that now there is a difference between taking, suppose I was doing sharp K smoothing, so everything is just, I just have to worry about the K modes. Now there is a difference between saying there's a barrier height and I have to multiply this walk by the growth factor, but that growth factor depends on K. And so it's changing the shape of the walk because of the K dependence of the growth. Yeah? So now I have to be a little more careful about how I treat the walk and the barrier and whether I can exchange growth in the barrier for growth in the walk. Okay? So if you're interested in that problem, talk to me later. Yeah? I'm doing the standard case, right, where this complication is not there. Okay. So we have a model that is going to give us the entire merger history of an object, of a point in space. No? So with a point in space, it's going to be the evolution of the mass around it. Yeah. The barrier is always constant, but again, that's just a detail, right? If the barrier was instead some shape, we would play the same game.
So what would it mean to have a barrier which is a different shape?
So for example, if you do ellipsoidal collapse, then it turns out that so the fact that it's there's an external shear field makes some effect on whether you can form a halo, and this one didn't get plugged in. Whether the object can collapse or not, it's really not plugged in. Just a second, I don't want to lose the signal. Now it's fine. Okay. So you can ask so there's a certain, the shear will help or hinder collapse, okay? And then you can ask how likely is the shear to have a big value or a small value? And the shear is more likely to have a big value on small scales than on big scales. The universe is isotropic. So on small scales, there can be small shear, but on very big scales, no. And so if the shear matters, the shear makes a bigger deal at small scales than at big scales. So that changes the height of the barrier. There's an effective barrier height. And on average, it's higher for small masses than for big. But again, that's just the detail. It's not changing the structure, right? It just makes it more painful to solve when you have a moving barrier, but the logic is unchanged. Okay. So as you said, the height of the barrier is a clock, okay? And the reason that, so it's a clock, and I did not write time here. I always said growth factor. And that's because if you say growth factor, then a lot of cosmology dependence is taken away. If I had put on here how many billion years, then I would have got big differences between standard CDM and lambda CDM, okay? But by writing it as growth factor, I don't have to do anything with the walks. They're done, okay? Similarly, this axis, I've been talking about a smoothing scale, and I've been talking about mass inside the smoothing scale. But I could equally well, instead of talking about smoothing scale, I could talk about the variance of the density field in the smoothing scale, the thing that was called sigma squared R. Yeah? Because sigma squared R is some integral over the power spectrum. This thing, okay? And so this is always a monotonic function of R, which means I can, the monotonic thing is as a function of R, sigma squared is always doing something like this. The universe is homogeneous on large scales, yeah? And so if I choose to plot on that axis sigma squared instead of R, then the translation between r and sigma squared depends on the shape of the power spectrum. But in terms of sigma squared, all Gaussian random fields are the same. Okay? So the translation, if I plot this in terms of sigma squared, then the translation from sigma squared to radius or sigma squared to mass, that depends on power spectrum because of that. But this picture is now independent of power spectrum and is independent of cosmology. So it's very powerful because you can analyze all these different models with this same picture. Okay? So one way to see this pretty clearly is to say, so let's not do this axis, let's just do the time. Okay? So the claim is that if I have a Gaussian field, so I picked my K modes, I put them down, and now I decide to run my simulation with lambda CDM, or I run it with standard CDM, with Einstein de Sitter. Okay? So this picture is saying, because the Gaussian field is the same, the objects that form in both simulations will be the same. The only difference will be when you express in years what the set of objects is. No? So after 1 billion years, the mass is this. After 2 billion years, the mass is this. And after 10 billion years, the mass is this in Einstein de Sitter. In lambda CDM, the steps for the mass will be the same, but not at the same number for the years, because I have to translate the growth factor. And the sort of nice thing about that is what is happening with the lambda CDM growth factor. It freezes out, right? It stops growing. So Anjan did the calculation, and he showed, that eventually in the far future, the outside universe is expanding exponentially away, and the growth has stopped. And so that means this barrier in lambda CDM, it drops with time, but it drops slower and slower, and eventually doesn't drop anymore. Which says there's a time when objects don't change their mass anymore, which is correct. Whereas in Einstein de Sitter, the barrier would keep dropping, and so those other more massive things would grow, right? And so that's the sense in which this is picking out all those things that will be true in different cosmologies and different power spectra, and they're all encapsulated in these variables very simply. Okay? So the variables are the overdensity in linear theory, so with the appropriate growth factor, and not mass or volume, but variance.
More massive things will grow. It means it will expand or it will decrease or reduce.
So in the initial conditions, because we're calculating everything from the initial conditions, bigger radius means bigger mass. Okay? But that bigger mass will collapse to be 200 times the background density at the present. But we're analyzing everything here in the initial field, because the goal is to predict from the initial field what the final objects will be. So that's why, in this case, bigger smoothing scale means bigger mass. But how much bigger mass, that depends on the shape of the power spectrum. Okay, so cosmology and power spectrum. So both those are taken out if you work in these variables. Okay, so now our goal is to calculate for a given barrier. We want to calculate how many walks cross here and how many walks cross here. No? Because the fraction of walks that cross here, we will say that's the fraction of mass that is in objects of this variance, so this mass, compared to here. Okay? So now how can we calculate this? So the first thing we'll do is we'll do a very simple thing. We'll pretend that the walks are not jagged. We'll pretend that the walks are very smooth walks. Okay? This is a little bit like if with a Gaussian field or with Gaussian things, with error bars, you say 1 sigma, 2 sigma, yeah? So this is like saying, suppose the walk is a 1 sigma walk. That means that on this smoothing scale, it is a 1 sigma fluctuation. On this sigma scale, it is a 1 sigma fluctuation. On this sigma scale, it's still a 1 sigma fluctuation. Okay? So what do I mean by this? So let's think a little bit more. What does a Gaussian statistics mean? The Gaussian statistics means if I go to every single position in space and I draw a walk for each position in space, then I will have a whole family of walks. If I take this smoothing scale, then I can make a histogram of the walk heights. That histogram will have a Gaussian shape, and the width of that histogram will be the sigma squared, which means this axis. Yeah? And so if I take a bigger variance, smaller smoothing scale, I will still get now a Gaussian distribution of heights, but the Gaussian is broader because the universe is less homogeneous on small smoothing scales. And this number here is telling me the width of this Gaussian. Okay? All right. And so if this is sigma squared, this height, the width of this Gaussian, one width, will be the square root of S, will be square root of sigma squared. No, that's what we mean by the width of the Gaussian. So that's why I've drawn curves that look like they're doing square root. And the square root you should anyway have in the back of your head. If you were doing random walks, then everything goes as square root of time. Diffusion, the distance something diffuses is square root of time. That's the same thing. Okay? That if you had lots of independent steps, then you would grow as square root of time. It's just here I'm drawing very smooth walks because I'm imagining incorrectly just to see the logic. I'm imagining that something that is 1 sigma from the mean on this smoothing scale is 1 sigma mean here too, and here too, and here too. And if it's 2 sigma from the mean, then it's this on all scales. And if it's 3 sigma on all scales, it's this. Okay? And the real walks are not like that. They're more like what I showed before, right? But just to see the calculation. So if we do that, then what would you say? You would say, well, the fraction of walks that crossed this barrier at big masses, so small smoothing scales. So at a smoothing scale smaller than this, a smoothing scale bigger than this one, variance smaller than this one. This fraction of walks is the same fraction that are above delta C on this smoothing scale. Because to arrive here, you had to have crossed earlier. Yeah? So the quantity I'm interested in is the fraction of walks that have crossed by some scale is equal to the integral over the tail of the Gaussian. Okay? And so the fraction of walks that have crossed, how do I want to say this? So this one is saying the tail of this Gaussian, the tail of the Gaussian is an integral over all the walks that crossed at this scale, or this scale, or this scale, or this scale. So Fs is the fraction of walks that crossed at S. And then I want the probability that you are above the threshold, probability that you're above the threshold at this smaller scale, given that you crossed earlier, meaning that you remained above the threshold. And in the example I'm showing here, if you're above, you're certainly above, because you never go down again because I removed the randomness of the walks. Okay? So in the example that I've shown here, this probability is 1 for all S. Okay? So that's one simple approximation. If it is equal to 1, then I can do the derivative of that Gaussian with respect to little s, the tail of the derivative of the error function. And I will get something with the Gaussian and the fact that I took a derivative. And that will equal the fraction that I want. Okay, so that will give me the mass fraction. Okay.
So So you're making bins on the r-axis.
Yes. The r-axis, which is an m-axis, which is an s-axis, and so it's really the sigma squared axis.
And for each bin, you're taking the proportion of crossings which are over that line.
Yeah.
So for each bin, you're integrating over the tail, given that it didn't cross before.
No, now I'm doing I'm doing a simpler thing, right? I'm saying, if I look at this walk, right, then there's some fraction of all the walks that are here, that are crossing this for the first time. So that's this term. This is the thing I want, and I'm trying to get it by doing something else that I can calculate. Yeah? And the thing that I can calculate is this argument that if it crossed here, it is above there. Yeah? And that is avoiding issues of binning, right? Because if I have to bin, then you start to worry about what bin size. So it's usual in probability things. If you can, you calculate the cumulative distribution, and then you take a derivative so that you don't have to do issues with bin size. Yeah? And so we're doing the same thing here. Okay. So in this example, this was very trivial, right? So we could write it out. No, we have on the left-hand side, the thing that is written in blue will be the tail of the Gaussian, right? So it is the e minus x squared over 2 pi dx from delta c over the sigma to infinity, right? That's the blue guy. And this sigma is the square root of a little s. And this one, we said, is the ds fs from 0 to little s. And this other probability is 1, because we've done the very smooth walks. So if they crossed, they remained above. Okay? So now I can do d by ds of this. And if I do d by ds of this, I will get e minus delta c squared over 2s, 2 pi, and then d by ds of delta c over square root of s. So I will get the delta c square root of s, 1 over 2s. Minus sign. Okay. All right. And this one, okay. I would get the minus sign from taking the derivative, but this was the lower limit of the integral, and so I will get this as a plus. Okay. And this one, if I take the derivative, I will just get fs. So that's my mass function. My mass function is a Gaussian with this extra piece. This thing is called the Press-Schechter mass function. It's not derived the way Press-Schechter derived it, okay? But I'm deriving it this way so that you can see the connection to how we now think of the problem, okay? So their solution corresponds to walks that are completely smooth, that are not random, okay? So there was a big fuss after they did their paper, in their paper itself, which came from the fact that if you integrate this over all s, you should get, or the assumption was you should get all the mass in collapsed objects, and the integral of this is half. And they didn't know why it should be half. They had a prejudice it should be 1. They had a prejudice everything should be in collapsed objects. So they arbitrarily multiplied everything by 2. Okay, so this is called the Press-Schechter factor of 2. In this construction, you can see where it's coming from. In this construction, half the walks, they went down. So they never ever cross, because it's Gaussian statistics. That's the factor of 2. Okay?
So how do we know it's exactly half?
If we just do this integral. So, yeah, so now you can just do that, you'll get half. Okay. And because it's all just Gaussian statistics, or another way is Gaussian is symmetric, no? So half the walks are above and half the walks are below. Okay. So that's the Press-Schechter factor of 2. So the thing that they have done wrong, okay, they should not have multiplied by 2, because the thing they really did wrong is these things are jagged, and they ignored that. Okay. We still call it the Preschechter approach. Why? Because at the time they wrote their paper, there were the prevailing thinking was halos are virialized objects, completely nonlinear. If they're completely nonlinear, virialization, virial theorem means you have lost all memory of where you came from. And so the assumption was, because of that, you will never, ever, from the initial field, calculate nonlinear statistics, nonlinear objects, right? And so their insight was to realize that it's true that the object itself is virialized, but the abundance of such objects, that's not erased. Yeah? And so that's what they're using, right? So they're using explicitly this fact that the Gaussian, that the field, nothing moved very far, and so I can really use the initial field to tell me what the final field will be. Yeah. Okay. All right. So that means the name of the game is to try to write down something like this. Okay. But if I try to write down something like this, then I again run into a problem, which is, and now I need to know the conditional distribution of having a certain height on some scale, given the first crossing on some previous scale. And I didn't know how to calculate first crossing in the first place, so what do I do? Okay. So one approximation is to say, well, maybe I can replace this condition that it crossed for the first time on the bigger scale with simply that it is this height on this scale, whether or not it crossed previously, meaning at some smaller scale, so smaller S, bigger smoothing scale. Okay, so now let's ask, when is this a good approximation? Okay. So supposing we were doing the walks that were truly random, so that the steps are actually independent. If the steps are actually independent, that means that if a walk has arrived to here, then when it takes the next step, you toss a coin to go up or down, because how you arrive there doesn't matter. Your next step is an independent step. Okay? And so that means that indeed, if you are this height, if you are height delta C at S, whether it was the first time or the second time doesn't matter for this quantity, because there's no memory of where you came from. In the jargon, the walks are Markov. Okay? And so that means you really can write this. But you can do even better, which is that if I'm here, okay, and now I'm going to take random steps to go up or down, okay? So then I'll take random steps to go up and down, random. When I reach here, this scale, then half of the time I'll be above and half of the time I'll be below, because everything is just random. Okay? And so that means, again, this probability, the probability that you will be above this value, you will be above this line on this scale, given that you crossed this line on some earlier scale, that is half. So instead of 1, it has become half. Okay? So the way I've described it is not the way it was first derived, but this was derived by Chandrasekhar in the 30s. Okay? So not in this context, of course. And this had been derived previously for truly random walks, for Markov walks, by an economist for modeling the market. Okay? Okay, so we've changed this equals 1 for it equals half. So if I come back here and if I put it equal to half, that means I should put this divided by 2. That's putting that probability as half. So then I will have this divided by 2. And this divided by 2 is that 2. Now everything crosses. Because they are random, they are jagged. And so there will be some scale at which, eventually they will all cross. And so this has fixed the factor of 2. by allowing the randomness. But this is for a very special smoothing filter, where the steps were Markov, were uncorrelated. Okay? And so our solution is going to be somewhere in between. So this showed Preschecter, they screwed up. They should not just multiply by 2, but it doesn't matter because you should multiply by 2 for this smoothing filter. Okay? So there is some justification for doing what they did. So the paper in 91 was deriving this factor of 2 in this way. No, again, not in the language I've used, but that was the paper in 91. Okay, was to find this factor of 2 by saying you get the factor of 2 if the walks have random steps, have uncorrelated steps. Okay? And so that means that our problem is the one where the not completely smooth, nor totally uncorrelated, but somewhere in between. Okay? And so I've given you the Preschecter mass function. And so our problem is to calculate this more complicated thing. So how should we think of it? So the usual way to think of it is to say, oh, I have to have all these steps, and I want to check that if I reach the barrier here, I want to check that all the previous steps, they were all below this barrier. So I can write out the path integral, right? I can write probability that delta 1 is, so I can write the joint probability of the P of delta 1, delta 2, delta 3, on scale 1, 2, 3, 4, 5, 6, 7, 8, 9. I can write that big joint thing. And then I can say, oh, now I have to put the condition that step number 1 was below delta C. So an integral, right, below delta C, below delta C, below delta C, below delta C, and finally above delta C. So I can write it formally, but it's a real pain because it's basically an infinite dimensional thing, right? So how can I treat this? And so the insight is to say, when you're thinking about correlated steps, what you should do is you should think that after all you have a curve. And so instead of thinking of the random walk as a set of heights on different scales, think of it as a height on the scale you want, and then a Taylor series, because you can describe the curve in terms of that as well. Yeah? So do that. Think of the curve as having a height and a slope and a second derivative and a third derivative and so on. Okay? So why is that a useful thing to do? It's a useful thing to do because our goal is to say, if I'm the right height, I want to check if on some earlier scale, if I've already crossed. And now, if I'm thinking about the slope of the walk, the height and the slope and the third and fourth derivative, but let's just think about the slope. If I think just about the slope, then if the walk should not have crossed before, it means it should cross going upwards. And so by requiring that the walk arrives at delta C going up, I have built in a long-range correlation. So it's an efficient way of putting the condition that all the other steps should have been below the barrier.
But this checks only for the previous step, right?
Okay, so now I'll write formally. So the idea is just this, that if I impose a constraint on the slope, we'll see, right? Because if I have to extend it to all the steps, I have not gained. Then I still have an infinite dimensional Gaussian, right? Yeah, so in principle, they're all the derivatives, but we don't want, right? So the question is this a more efficient way to truncate, okay? So that's what we're going to do. We're going to write out the problem. So we're going to first ask how will we use the first derivative, then we'll ask how to use it, So what do we want? We want so our first crossing, we would write now as we want the probability that the height is some delta C and that the derivative has some value. We're going to say it should be crossing upwards. Okay? But let me write what the conditions are, okay? Because the game is what should we put as the limits of the integral, okay? Because we know how to write this joint distribution. Okay, it's just something from Gaussian statistics, so we can write it. So what's our condition? Our condition is that the walk is going upwards, so the derivative should be positive. Okay, and what we want is that let me write this as two separate conditions and then derive this guy. What we really want is that delta on smoothing scale S is above delta C, and delta on smoothing scale S minus some delta S. So on some previous step, some small previous step, this should be less than delta C. That's what we really want. Okay. Now this guy I can write as delta at S minus delta of S times what I'm calling delta prime. No? I wrote this as the Taylor series. And so it's a delta at the scale S, then how off I am from delta, the first derivative. And then there's second derivative and third derivative and fourth derivative. So that's what I mean by the Taylor series. And so we have these two conditions. Delta has to be bigger than delta C, and delta minus this thing with the first derivative has to be less than delta C. So let me keep, so I guess that's all I've written there, right? So delta I just put those two conditions together to say delta has to be bigger than delta C. And the other condition is the delta minus delta S has to be less than delta C, which means that delta C plus that condition, delta has to be less than that. Okay? So these are my two conditions. So that means this is, I put this as the limits on delta, and I put this as the limit on delta prime. Okay? But this limit, I'm taking delta from delta C to delta C plus a small number because I will take the limit of a tiny step. And so that means that this guy I should write as follows. I should write, maybe I should write it again here. So we have the joint distribution of P of delta and delta prime, d delta prime, with the limits and this one is 0 to infinity. So we have this guy. This guy we will write as P of delta prime times P of delta given delta prime, Bayes rule. So this guy is going to sit outside because it doesn't depend on delta. And then we will do this guy. But this guy is going to be P, because this is very small, this guy is going to be P of delta C given delta prime times delta S delta prime. Okay? That is going to be the result of doing this integral over delta. It's the, can you see that? It's like I would evaluate this thing here and evaluate this thing here, and then I have to subtract the two values. So I would take this thing, expand in a Taylor series, which will be this with this correction, and then I will have subtracted the zero order term, right, from here. So that's what I end up with. So I will end up with this, and I still have to integrate the P delta prime, d delta prime from 0 to infinity. That's the expression that's written there. Yeah? And so the expression here is taken one more step. There I have a P delta prime, delta C given delta prime. Now I have to integrate over delta prime. So I can make delta prime conditioned on delta C and take the delta C out. So that's what I've done here. Okay? And this integral is from 0 to infinity. And so this is just some Gaussian with a mean that depends on delta c. So it's an integral that is a trivial thing to write. Okay? Okay. So this is the first approximation to the correct answer. Now, in principle, we should take care of the higher derivatives too. And so we can ask, but it's a huge simplification, right? Because now we go from what's essentially an infinite dimensional Gaussian, multivariate Gaussian, to 2. Okay? All right. So doing this is useful because if I want to do a barrier that has some other shape, then I just put my conditions here. No? Now my delta prime has to be above, has to be crossing the barrier. So if the barrier is also increasing, then I also have to put, has to be increasing more steeply than the barrier. And similarly here, there will be a more steeply than the barrier. That's all. So it all goes through very easily. Whereas for the random walks with uncorrelated steps, a barrier that changes shape is very painful to treat. There are only 2 known analytic barriers. 2 known barriers for which the first crossing has an analytic expression. Yeah.
So in that case, your limits on your integral over there would change with the barriers.
Correct.
Delta SC would be a function of R.
So delta C will be a function of smoothing scale, that's right.
And then when you differentiate it, you'll have a complicated...
Yeah, it's actually not so complicated. So it turns out, but it's a straightforward thing. Yeah. Okay. So this is the result of writing the first crossing, of doing that integral over delta prime. Okay. You still get the Gaussian E minus delta C squared over 2. Okay. So this nu is the delta is the same Preschecter variable, right? Did I erase it? The delta C squared over S. That is the thing that is nu squared. Okay. And so this piece is like the Preschecter piece, and this is the correction to Preschecter. Okay, so this is a correction that is going to unity at large nu. Large nu is, so nu is, I should have defined nu here. Huh? Nu is delta C over sigma. The small sigma means large smoothing scale, means large mass. So large nu means large mass, because the sigma is in the denominator. Okay. So large nu is large mass. So the large mass objects are exponentially suppressed, and smaller mass objects are much more abundant. Okay, but and so in Preschecter or in Bond, there was one number that mattered, which was the delta C over sigma. Then from this variable nu, you would say, okay, now I have nu, a Gaussian in nu, or Gaussian cutoff in nu. This nu has encoded in delta C with a growth factor. So the cosmology is entering there. And to get sigma to mass, the power spectrum is entering there. But otherwise, this is universal for all cosmologies and all power spectra, right? And then I can convert to mass and time by converting nu into mass and time. And so now when you put the derivative, then there's a parameter here that describes, it's not a free parameter, it's a thing that is the property of the Gaussian field that is describing the correlation between the slopes, and so the derivatives and the delta itself. Okay. And so in this sense, the Preschecter would have said the mass function should be the same for all Gaussian fields. And now this will, this one is saying that's not quite true because different Gaussian fields will have different correlations between walk and slope, height and slope. And so there will be a second term. Yeah. So you're looking at scale-free simulations. The scale-free simulations, the prejudice had been that if you work in this variable, then the mass function should be independent of power spectrum. And this is saying that is not quite true because this number is different for different power spectra, and so they won't be the same. Okay? Okay. So that's the mass function, okay? It turns out that this actually works very well for cluster mass halos, and it only starts to fail at around galaxy mass halos, okay? Then you can account for other crossings, but in the school I won't do that, okay? So I just wanted to give you the logic which we use to calculate things, yeah, to get the mass function. There's a bit about warm dark matter, but we're close to T, so let me just skip this. And I've made the point about the simplification is evolution from cosmology, statistics from power spectrum, okay? And let me just jump a little bit to so I have the test to show you that it all works a little later. So we'll see. But this works well. Okay. The real one is closer to the correlated one. Yeah. So that's closer to the right thing. Okay. So a quick sketch of the logic and then the calculation, right? So remember, we already know that although we're using spherical collapse, the real spherical collapse is that each one of these guys is doing their collapse while they're all collapsing together, right? So this is really what's going on. It's not one smooth thing that is collapsing, okay? So what's the picture? So the picture is something like this, okay? Suppose we choose a piece in a Gaussian field, and we have found one of these patches that is density is delta C, okay? So that patch, it can have a lot of substructure. Meaning when you smooth on a smaller scale, then there will be some regions that are dense inside it. It need not be that the center is the densest and it's a smooth profile like we assumed for the spherical collapse calculation, okay? In fact, it's lumpy. But the lumpiness is given by statistics of a Gaussian field, so by the shape of the power spectrum. Okay, now what happens? So each of these guys does its spherical collapse. And because this guy is also doing its spherical collapse, as these are collapsing, they will move towards each other, they will move towards each other, they will move towards each other, and then they will merge. And so if this is the initial spatial distribution of the patch, like these circles represent the overdense regions that maybe at redshift 1 were the collapsed halos of this redshift 0 object. And the idea is as this shrinks, they all stay inside here, right? And they will merge with each other. So that was the thing that we were drawing the sketch. You know, there was the yellow thing that was showing the mass increasing with time. Now let's see how we use even more of this information, okay? So this is saying that if I have this big object, so this big ellipse here represents that large mass, okay? These represent the pieces that large mass was in at some earlier time, okay? And so now the idea is that as this guy is shrinking, then the nearby things will merge with each other first, because this is cold dark matter, so nothing is moving. So the only thing that is happening is that volume is shrinking, and so they're getting closer to each other. And so that means these two will merge with each other. And then eventually they will merge with each other. While that is going on, these four, they will all merge with each other. They're all equidistant, so you know it was not like this. There was all to here and then nothing more, right? And that one is all 8, and then nothing more. And then the whole thing has collapsed, so then they all merge with each other. Yeah? So that means that in the statistics of the initial field is encoded the entire merger history of the object. Okay? So in principle, we can extract this information. That's what we're trying to do. So this is where you see it's really something that works for CDM, for cold dark matter, because we're assuming nothing is moving around, and the initial statistics are giving you everything. Okay? If neutrinos was the dark matter, then you know they would have all moved around, and I couldn't play this game. So they're not moving very much. Well, so remember, we said typical motions are 10 megaparsecs. These patches are not 10 megaparsecs. They're smaller than that. Okay? So in principle, what I'm doing is an extrapolation. It's not okay. right? Things could have moved. But the idea is that we are pretty sure from spherical collapse that if I have found the region that is going to shrink, okay, then it means nothing escaped from it. And so this is okay. It's telling me that the things have moved around maybe inside this patch, but they didn't go outside to another patch.
Is your goal to kind of, get information about the initial spatial distribution?
Yes, so I'm going to do this in a few steps. My goal is to get, so the first idea is that if I know something about...
if you know the initial spatial distribution, you can, of course, find out what it will finally turn out to.
Right.
But the reverse is not necessarily true, right?
That's correct, okay? So my goal is to go from the initial forward.
No.
Okay, not vice versa. Yeah.
What I feel that then which type of, because you can arrange all sort type of bodies in many manners, no? There are
Correct.
so many ways. So which type of ways we should choose and which we should neglect and...
So it is completely, I have no freedom in this. It's completely given by the statistics of Gaussian field. Gaussian, okay? Yeah, right? So Gaussian fluctuation, so what do I mean? I mean that for a Gaussian field will tell me that this was one possibility. But over there in the universe, if there was a similar size patch, it could be that I have to draw all those balls all in the center. Okay? Somewhere else, it would be different again. Okay? And the Gaussian field tells me how many are like that, how many are like this, how many are like that. All that is given. There's no freedom.
For the final patch, the density is same, but the radius is bigger.
For this final patch, so we're looking at it in the initial conditions. So this is kind of a big radius, and then it will shrink. I mean, it will expand and shrink, right? And if we think in co-moving coordinates now, it will just shrink until at the time when it virializes, it is 200 times the background density. Similarly, these, when they virialize, they will be 200 times the background density when they virialized, meaning they will be more dense now than this, okay? And so that means that we can, in fact, extract the entire merger history of the object, okay, from the Gaussian field. Now I want to make a slight leap, okay? My leap is like this, because my goal is a spatial distribution. And the merger history is interesting anyway, right? Because I would like to know, if I have a cluster that is 10 to the 15 solar masses today, that cluster, did it have a recent merger? Was it half its mass at redshift 0.1? Or what fraction of clusters were half their mass at redshift 0.1? How many were formed by mergers of equal mass objects? And how many were small things being accreted all the time? Okay? So things like that we can address from Gaussian statistics. So we can make a connection to observations in this way, right? We can start saying, some fraction of clusters should appear like they had a recent merger, some fraction of objects, how does the accretion rate of an object depend on its mass? So do clusters assemble their mass similarly to galaxies? So you can address all these questions. And I'm not going to do that here. I want to, although we could, right? I'm instead going to play the following game. When I describe this picture, I describe this as redshift 0, 1, 2, 3, okay? But I could have described it as this is redshift 0, and in the future, everything will collapse. And redshift 0, this is the past. Okay? And I could play a game like that. If I do that, then you would say, look, this redshift 0 guy is like the progenitors of the future object. And so if I can quantify how many pieces is the future object in, no? Is like I said, a 10 to the 15 solar mass object, is it in two equal mass pieces, or is it in many small mass guys? That means I can do the same by saying I have currently a patch that is 10 megaparsecs in size. It is not virialized. It will virialize in the future. Okay? So that means the present is the piece of the merger tree of the thing in the future. And so if I know how likely it is that this guy was in 2 equal mass pieces versus 10 small pieces, that's telling me about the variance of the counts of the equal size pieces or of small pieces. No, it's telling me something about the distribution of masses in a 10 megaparsec patch. Okay? And so that means that the same statistics of the merger history, if I am careful, I can interpret in terms of spatial statistics today. Okay? By saying this is still, today this is still a big region because it hasn't collapsed to make the virialized object. So now I know something about the distribution of halos in biggish regions. Yeah? Because I could have done the merger history of this object. So that means this too is built into the Gaussian statistics.
Is there any limit that all the time they have to merge, merge and merge? At some point of time they have to stop and the final object is there, no? At what time? Or
in an Einstein de Sitter universe, the linear theory growth factor is always increasing. So that the barrier I was showing you, that will always decrease. And so the object's mass will grow and grow and grow always. Okay? Whereas in lambda CDM, the growth factor freezes out. And so the object's mass will grow and grow and grow, and then it will not grow anymore. Okay? And so let's do the same discussion here, right? So I make my initial conditions. So those are my initial conditions. Now I run the simulation. If I run the simulation with Einstein de Sitter, then the simulation goes through this step, this step, this step, this step. If I run with lambda CDM, it will go through this step, this step, this step, but because the growth factor freezes out, I never reach that step. And so structure stops there. But the sequence is all the same given to me by the Gaussian statistics. It's just I never reached the final stage. Yeah? So it's a big idealization, but it lets you calculate things that are not accessible otherwise. Yeah?
Can you elaborate more on the initial conditions?
Okay, so for the initial conditions, we had done things when we set up the formalism for Gaussian. We said we know how to write things like delta 1, delta 2, delta n. We know how to write some joint distribution like this. Let's just take 2, okay? Now, when we did this, we did always, it was as though I'm talking about delta at this position and delta at this position. But I can equally write, because of convolution of Gaussian is Gaussian, I can instead say I want same position, 2 different smoothing scales. So now this means smoothing scale 1 and smoothing scale 2 at the same position. I could do that. And so something like that problem is, given that the large delta 2 equals delta c, I can ask what is the distribution of delta on the smaller scale. And we know how to write that, no? Because we know how to write the correlation between delta smooth with 2 windows. That one is the integral over the power spectrum with the 2 different smoothing windows, that's all. So that's why when I set it up, I said it's important that we can write the general thing with different smoothing windows, different scales. Yeah? So sigma squared is this. But if I want the same position in space, but 2 different smoothing windows, then I would just put smoothing 1 and smoothing 2. Yeah. And so now I can do delta 1, delta 2, delta 3 on the small scale, given delta equals delta c on the bigger scale. I can do that. I can write it out for Gaussian statistics. So you can all just write it out. Yeah. And so this fact that you can write conditional distributions is ultimately what we're going to use to do the spatial distribution. Yeah? Because everything is still just going to be some Gaussian. Yeah? If you put a condition, then you will just change the mean of these guys because of the condition, and you will change the variance a little bit. And so now if I wanted to do, so we'll draw a picture like this in a second, but I could play the same random walk game versus smoothing scale. Before we were doing the problem where all the walks start from the origin and they have to cross some delta c. But I could choose all the walks that, of all the walks that are doing this, I can take the subset that all pass through this point. So delta has some value on some scale s, and then they continue and they cross. So I can ask what is the mass function of the small scale halos given that they're in a large scale halo. Yeah? Or if you want, the merger tree problem is, given that for delta c at redshift 0, I know I've crossed here, then I will cross on some smaller scale the higher barrier. And so now I know the mass function of the subclumps, the things that collapsed at some earlier time, of my redshift 0 10 to the 15 solar mass object. Yeah? And it's just the same random walk problem, but now a conditional one. And so the whole analysis that I did here, now I put the extra constraint, right? That I was writing some Gaussian distribution. Now this one is given the large scale, and this one is given the large scale. It's just an extra constraint. Otherwise, everything is still a Gaussian. Everything is still a Gaussian. And so nothing changes, right? The logic is the same. It's just what you put for the values of the Gaussian that is adjusted. Okay.
From this model, you said that the cluster mass at different redshift will be different.
Yes.
So can we expect this trend in observation as well?
Yes. Yeah. And so we see the masses change. I'll show you that comparison soon. Maybe I should have shown you that first and then do this other stuff. So let's let me see if I can. So this is the number density of objects as a function of their mass in lambda CDM. So the simulation was run, and the black is the halos at redshift 0, then at redshift 2, 5, 10, 15, something like this. Okay? And so you can see that at early times there are only small mass halos, and then at later times there are more and more massive halos. Yeah? And what this is trying to describe, so the curve is this kind of prediction for this. Okay? And so it's describing the increase, the change in the mass function as a function of time, the change in the abundance of objects. So remember I said it drops exponentially, so the massive objects are much rarer than the less massive objects. And that scale is just changing as time goes on. Can we construct some
generalized lessons of mass of halo with the redshift?
Yeah, we can do mass accretion rate of the halo with redshift, yeah. And so, so if we took one of these 10 to the 15 solar mass halos, then we could make a plot of what was its mass as a function of time at the previous outputs, and we can compare with the predictions of this. It works pretty well. So I'm not showing you those kinds of tests, but they've been done. Yeah. Okay. Okay. So a quick thing, I showed some of you this picture before and I commented on it earlier, but let's quickly look, right? So this is the halo at redshift, the 8 different halos at redshift 0. And what we're going to do, so the size is 2 megaparsecs. So look at the central piece, the central 20 kiloparsecs, the central 1%. Okay? we'll take those particles and we'll ask, where were they at redshift 1? Okay, so this whole thing was bigger, in co-moving coordinates was bigger. Yeah. Okay, so each of these halos was more extended. And the blue particles are the ones that were in the center at redshift 0. You can see that they're in the center of the redshift 1 guys. That's the same guys at redshift 2. Now all the pieces this is in are in smaller pieces, but the objects in the center are in the center of the smaller pieces earlier. So this was what I was saying about the rank ordering of the binding energy. The blue are the ones that are in the center at the end. But you can see that they're not all together, but they're at the center of the objects that exist at any given time. Yeah? Okay, so yeah. This is what?
So, blue regions are always inside red regions?
Yes.
So, is it due to the effect of smoothing?
So this really is, I mean, you have particles, right? So they're just where they are, right? But I guess what I'm trying to do with this plot is to show you, I should think of the blue regions here as these things. No? So these are the smaller guys that collapsed earlier. And then they're going to collapse, and they will all sit right in the middle at the later time.
I was talking about the boundary. If you look at the boundary, these denser regions.
Sorry, which boundary? You mean of this? Yeah? Okay.
Is the color coding different at redshift 0 and 1? Because yellow at redshift 0. Yeah, so in the middle there is yellow color.
Oh no. So you're okay. We should have shown you where the blue are here, but because it's 1%, it's like a pixel, and so you don't see it. Yeah. Okay, so that was just to motivate again, right? That this spherical hierarchical spherical collapse on all scales is not far from the truth. It's not perfect, but it's not far from the truth. Okay. Okay. So
in last slide, if we look it into term of redshift, and if I just translate it in the term of time or years, then from redshift 0 to 1, it take around 8 to 10 billion years.
Mm-hmm.
So, and for redshift 1 to 2, it's around hardly 2 billion years.
Mm-hmm.
So in 2 billion years, they are going to grow in this way, and suddenly that's not a huge change. So how to explain it?
yeah, why? Are we in an Einstein de Sitter universe? Structure started freezing out. And so from redshift 1 to redshift 0, the change is less than from 2 to 1.
So all these huge structures, like we can say that in present regime, they are kind of virialized or stable.
Yeah, so in general, that's a safer statement for the slightly lower mass objects. The most extreme objects at any given time, they're doing something extreme, right? So they're the ones that are currently merging and stuff like that. Yeah? And it's kind of nice, but you can quantify that statement also exactly just from these Gaussian statistics. Yeah? So you can see that the most massive objects are kind of being made from the most massive objects at any given time, and you can do all that stuff.
Same as we are having the present, because all the structures they have been just formed and they are virialized.
Pretty much. There's still some time if you want more company, but we are running out. Okay. So there was some fear or relief about whether Andromeda will collide with the Milky Way galaxy, yeah, because of lambda and so on. Okay. 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 So now I want to motivate a little more how we will. So I've done the hand waving stuff for getting structure, getting spatial information. So one more slightly hand wavy thing to give you, another way to think of this in the random walk picture now. Okay, and then we'll do the calculation. Okay. So in the random walk picture, I want to, because now I'm interested in describing a patch that may not yet have collapsed, that in the future it will collapse, right? That was the motivation for thinking of using merger tree evolution to tell me something about spatial distribution. So I want something that has not yet collapsed. So I'm going to use this spherical collapse mapping. Okay? The nonlinear density is related to linear theory with 1.686. Okay. So the first thing I'm going to do is I'm going to rearrange this so that I get this by itself. And the reason I want to get this by itself is this is the y-axis when we do the random walk. That's the variable, right? I mean, divided by delta c, but that's the variable. Okay. And so that means that this is a 1 minus the nonlinear density is a mass over a volume. Okay, and I've raised to the power. And the mass over the volume, the mass I can relate is a monotonic function of the variance S. So, and the variance S is the x-axis of the random walk, the random walk picture. So this means that if I fix the volume, then I will get a curve which is delta 0 as a function of S. Okay? If I change the volume, I will get a different curve. So if I pick my volume to be 100 megaparsecs, then I will get one kind of curve. And if I pick the volume today to be 10 megaparsecs, I will get another curve. And 1 megaparsec, another curve. And if I pick my volume to be 0 megaparsecs, then I will get 1 minus infinity, because this is 0, the negative, so 0. So I will get this equals 1, which means delta 0 equals delta c. And so the flat line, which was our barrier before for making a halo, corresponds to this being 0, because the halo is in idealization has 0 size. And now I just want where this is not 0. Yeah? Okay? So it's the same random walk that I drew as before. And now these curves are for different choices of the redshift 0 volume. The one we had looked at before was the redshift 0 volume is 0. This one is 10 megaparsecs, and this one is 100 megaparsecs. Just to illustrate, that's a bigger volume. How do we know that's the bigger volume? Well, if we go back to this picture, when the nonlinear mass equals the nonlinear volume, so there's no density fluctuation, so that means that this guy is 1, then that's because this guy is 0, right? And so that means that from where this curve is crossing 0, that's telling me the Eulerian volume and the mass at which you're crossing through that, right? So this one, so large mass means large Eulerian volume and small s. Okay, so this 0 crossing is telling me what was the Eulerian scale that we're talking about, because the mass is the volume on that scale. And so to make it a little more graphic, before I had a yellow curve which represented as the constant barrier decreases with time. Then we had how the mass is changing as a function of time, the collapsed mass around that position, right? Okay. Now let's take the walk. The walk crossed the constant barrier on this mass, on this S, so this mass, okay? So that means that this is a halo that inside 10 megaparsecs, so it means the 10 megaparsec scale around it, there is this much mass. And in the 100 megaparsecs around it, there is this much mass. I just see where it first crossed. So I always do first crossed, right? Because spherical collapse is telling me that the thing has had to shrink. And I want to know the largest volume which has shrunk to make this, okay? And so that means I'm getting information about the profile around the halo, the evolved profile around the halo. In the Gaussian field, I can write out what was the initial profile around the halo. Now I get the evolved one by asking that this is the initial profile around the halo, right? This was the Gaussian field profile. No, this represents the halo, and this represents the density around it in the initial field. And now by saying I don't care about the initial field anymore, I want the final field, then I want to know when it crossed here, when it crossed here, when it crossed this barrier, and so on. And that maps for me how the mass changed position because of the density. Okay. So that means now I just have to be able to solve a moving barrier problem. But the formalism is fine. The barrier can depend on S, and I can do everything, so I can solve that problem. So now you can solve that problem, right? That's all you have to do. So let's think of a limit, okay? And the limit we're going to think about is the limit in which this scale is quite big, okay? And we're going to ask, let's consider two kind of walks. So let's go to the next one. We'll take two walks. One of the walks came like this, and another walk came like this. So both the walks, because they are crossing here, it means they're crossing delta C, so they both correspond to a halo today. Okay? But one halo is surrounded by, it's overdense even on the 100 megaparsec scale. And the other halo is in the middle of a void, not much around it. But the universe is homogeneous, and so at a gigaparsec scale, at the Hubble scale, it's back to 0. Okay? All right. So that's these two walks. But now let me ask a different question. Suppose I imagine all the positions in the initial conditions which pass through here. Okay? Then I want to know, given that they pass through here, how likely are they to cross delta C on this scale, or this scale, or this scale? So that's like saying, in a dense region, what is the distribution of halos? And in an underdense region, what is the distribution of halos? And we would solve it the way I wrote on the board. No, I would put the big delta. Now I would say, given that on large scales, delta is, on 100 megaparsecs, delta is 0.1. Or given that on 100 megaparsecs, delta is negative 0.1. Okay? And I will do this analysis by putting two different constraints here for the dense and the underdense region. I will get a different mix of halos. So I will get the environmental dependence of the halo mass function. Okay? And you can see by eye what is going to happen. So the walks that start here, so in dense regions, the walks will continue, right? And so most of them will cross more or less here, because they have only this much to travel. So they will all cross quite soon. Whereas this guy, all the walks that arrived here, they have very far to travel. And so most of them will cross around here. no? Because they have to take many steps before they cover this much bigger height. So the mass function, the masses in an underdense region will all be small. And the masses in an overdense region will all be big. Okay? So that's a non-trivial statement, right? So if I wanted to know what is the number density of halos of some mass, given the density, given the large-scale density, then the simplest guess might have been, oh, I should just say, the bigger region, if it has more mass, then I have more halos. But there's no change in the mix of the halo population. And this is saying for sure there will be a change. The dense regions will preferentially have massive halos. The underdense will preferentially have low mass halos.
Is it something like chameleon mechanism?
Chameleon, very good, okay? So it should be possible to use this argument because, so chameleon mechanism is in modified gravity. You're playing games with when gravity is modified. You want everything, to pass solar system tests. And so you're making gravity different on large scales. You're making gravity normal on small scales. And so there's some transition scale, meaning the environment is mattering whether this mechanism is switching on. And so this gives you a framework for doing that. There may be 2 papers in the literature that have tried to implement this, but it's not quite okay. So if you're interested, we should talk. Yeah. Okay. But so this is the language for trying to do that problem nicely. Okay. I'm just going to do it in standard gravity because even there it gives interesting results, right? So the crude statement now is, so we've already established that it cannot be that this is the case. Just because you have a denser environment has more mass doesn't mean you just have more halos. You actually have a different population of halos. They'll be all more massive. And so now let's imagine that although we could solve this problem for this constraint on any scale, let's suppose that we put the constraint on very large scales. The reason for doing that is that on very large scales, universe is almost homogeneous, so the variances are all small. The variance is small, meaning the walks, they don't actually get so high, right? The walks are all typically here. And if the walks are typically here, it means that the value of delta 0 is small. Which means when I put this constraint, then the constraint number is going to be some small number, which means when I get my final answer, that small number will show up. So I can do a Taylor series in powers of that small number. Okay? And so that means that the mass function will be the universal one plus correction for that small number plus correction for that small number squared and so on. So we can just do an expansion in that constraint. And that expansion, the coefficient of that expansion, that thing is called the bias factor. This is the linear bias factor because it's the term that is linear in delta 0. There will be a term which is delta 0 squared, delta 0 cubed, so that is called quadratic bias and so on. Okay? So you will get the description of how this function, the conditional function, differs from the universal one because of the environment. Does that make sense? Yeah.
So these are the 2 cases in this lecture. I have one confusion, like in overdense case, like it will form structure, that is understood. Like immediately you told that from the non-linear perturbation theory, the dense structure will go denser and the void region will go broader.
Yeah.
So but here it is counterintuitive in the sense like overdense region is going to make structures at some time.
So the overdense region is going to be made of lots of dense objects, so it means lots of massive objects, whereas the underdense region is going to be made of lots of low mass objects. So it's a bit like when I made this picture. And I drew things like this, and I said I want to know how many pieces things are in. It's a little bit like saying that might be an underdense region, and the same patch for an overdense region is like this, no? Because they're all more massive. All the sub halos inside it are all more massive instead of lots of small pieces. Does that make sense? And so in the jargon, we say the mass function is top heavy in dense regions, more massive objects. One way of thinking of this is to say, if you wrote this as a Taylor series, then this bias factor, this should be a positive number, or it should be a larger number if the mass is big. Because if this number is big, then it says if this is positive, then I have lots more of this mass. If this is negative, then I have fewer of this mass. I'm always multiplying by 0.1 or 0.01, right? And so this is saying that the bias factor is an increasing function of mass. And we will write down soon how to quantify the fact that it's an increasing function of mass. But you can see it must be from this.
Can you draw this plot for two different initial densities?
Two different initial densities.
Delta rho, delta 0 is different for two different halo. And what will be the path for those? So I guess the lines I haven't drawn there are the following. Suppose that I have, this is delta C, and if I am a dense region, then the paths, so there are many ways I can reach to be a dense region. And then once I've reached, there are many ways I can continue. Okay, so this is telling me, but the important point is they will all reach around here. That's what you were asking, or something else? If there are two halo with different initial values, initial density.
Initial.
Or density.
So this is the. So you have to tell me if the overdensity is on what scale. So I've drawn a picture where the overdensity is on some large scale. Yeah, and so I'm saying these are halos with a large initial overdensity, and these are halos with a small initial overdensity. Yeah. So yes, so I could have drawn. If I take halos of fixed mass, so I could arrive like this, I could arrive like this. I cannot arrive like this, because then I would call it a more massive halo. But I could arrive like this, okay? And so we would call this one represents a halo surrounded by an overdensity. This one represents a halo surrounded by an underdensity or by a void. And this one is a kind of average halo. Yeah? But all this is given by statistics of Gaussian field, so we can calculate all those probabilities. Yeah? And by calculating all those probabilities, you really just do this. Yeah? And then the correlations between these, they depend on the correlation matrix C, which depends on the power spectrum. Okay, one last idea is that we like to think that a dense region is, we can think of it as a effective omega, effective cosmology. If it's dense, then it will have, if it is an effective cosmology, it should have the growth factor of that effective cosmology. Okay, so nowhere did we say anything about that here, right? Here we're just using this picture that they have little distance to travel or big distance to travel. Okay, so let me ask, if we really can think of environment
as an effective cosmology. Okay? And so can I really think of this as some effective growth factor? Okay? And so the answer is yes, absolutely. Okay? And let me see if I can actually write this nicely, because it's quite illustrative. So what will happen as a result of doing this kind of thing is that the mass function was something like this with other stuff, right? There was the Gaussian piece, and then there was some delta C over S, this kind of thing. This was like the Preschecter guy. Now, if you start on some other scale, then this will become delta C minus delta 0, 2S minus S0, this S minus S0, S minus S0, delta minus delta 0. Becomes something like this. You shift the origin both of how many steps you have to take and of how high you have to go, because you're already some way. Okay? So it will be roughly like this. Okay? Now, for delta 0, let me write this as delta C over delta 0, 1 minus, delta C, I take out, delta C squared, and this becomes delta 0 over delta C. Okay? But, we have that fitting formula, and the fitting formula was that 1 plus delta is 1 minus delta 0 over delta C to minus delta C. So I can put this to the minus 1 over delta C. And this guy is this guy. And so this is 1 minus delta 0. This becomes, let me keep this here, but we'll now say that this will be like a delta C squared times 1 plus delta to the minus 1 over delta C. If we were doing things on very large scales, then the variance for a halo is much smaller scale, so much bigger value than the large scale environment. This guy is 0.01, this guy is order unity. So I can ignore this guy. So this is delta C squared over S, and I have this factor that I multiply my delta C squared. Yeah? And I should have squared, right? So that means this is like a growth factor that I multiply delta C. Okay? So this made it very easy to see it's like a growth factor. But then you can do the calculation exactly, and you find that it is exactly the effective growth factor. Okay? Because remember, this was an approximation that makes it easy to see the logic, but the calculation is exact. But the beautiful thing is, you didn't have to think that way to get the right answer. You get it from the picture. Okay? So it is true. You can think of environment as effective cosmology. You have to do it right. So the other nice thing about having to do this is the environment is effective cosmology, but let's think, what is the environment? So the environment, we said, it's an overdense region, 1 plus delta. So the density is background density times 1 plus delta. It doesn't mean omega is omega times 1 plus delta. Omega effective is not, because omega, you need also H. And because this is an overdense region, the effective H is different from background H. And so density is 1 plus delta, H is also modified. And because H is modified, omega effective is not 1 plus delta times omega, it's something else. But we can calculate that. Okay? What about lambda? Oh, you'll say lambda is the same everywhere in space. Doesn't matter if I'm in a dense region or in another dense region. It's the same value. That's correct. That is correct for lambda. But omega lambda cares about h. And so omega lambda is different. And so if you want a dense region in omega plus lambda equals 1, that dense region now has some curvature. Okay? So all that affects the growth factor, and all that is coming out correct for free from this construction. Okay? Okay.
Can you look into how the bias factor comes as a definition of bias?
Where did this bias factor come from? So we haven't calculated its value, but just for the logic, it's coming from saying where to calculate the halo mass function, we will do the same calculation we did as in the morning, but now we will put the constraint of the value of the environment. So now capital delta means the value on 100 megaparsecs. Okay? And that value will be some small number because it's 100 megaparsecs, so it will be 0.01, something like that. And so that means when I write out all of this, then let's do a very crude thing. Okay? So the very crude thing is we're going to get something like this. And then remember I said it was like the Press-Schechter times 1 plus times a correction factor. Let's forget about the correction factor because already there's a delta factor sitting here. Okay? So I can make a Taylor series expansion of this. Sorry, this delta, this is that big, the constraint. So it's the thing that I was calling this delta. It's like this. Okay? And so now I can take the ratio, so I can just do a Taylor series expansion with respect to this. So you will do, maybe this one is better to, yeah, okay, I can do like this. So I will have a 1 minus 2 delta 0 over delta c in the exponential. So that guy I will bring down because I will have an e to the delta 0 square, delta 0 over delta c multiplying by this thing. So that thing is the bias factor. Yeah, so this guy will be e minus delta c squared over 2s. Then the e to the 2 times delta 0 delta c, that guy is the one we're expanding. So that will be a 1 plus 2 delta 0 over delta c times the delta c squared over 2s plus higher order terms. Yeah. And so this stuff here was the previous value. That's the thing we're calling n of m. And this one gives delta c over s is the bias factor because s is a function of m. Okay. And so when s is big, because m is small, then the bias factor is a small number. And when s is small, because m is big, the bias factor is a big number. Okay, so that's the bias. Okay, so the thing that I've written here, this thing is correct for the sharp k walks. This is all exact for the sharp k smoothing. For the correlated steps, you have to do this, but the logic will be the same, and you'll get a slightly modified bias factor, but it's something you can calculate. Okay, so let's skip some of this stuff. We said write as a Taylor series. This is writing as the Taylor series. This is, again, writing as the Taylor series. So now we can define the overdensity of the halos. So we'll say, given the large-scale density of matter, is this value on this large scale. The overdensity of the halos is given by the ratio of the conditional mass function to the unconditional mass function. Okay, so that's the 1 plus b1 delta 0 okay, plus the higher order terms.
Okay, so this is the number of halos that formed given that delta 0 is already there.
Yeah.
And that's the total number of halos.
This is the average over all values of delta, so average over the full simulation box.
Them and you get an effective overdensity.
That's right. That's right. Yeah, so this is the overdensity that you had because you were in an overdense region. Okay? And so, so now we can do the cross correlation between the overdensity of the halos and the overdensity of the matter. Okay? And so if I want to do this, then we will say, oh, but delta halo is the same as B1 times delta matter. And so there's the B1, delta matter with delta matter. B1 is a constant. Delta matter with delta matter is the power spectrum. And so the cross correlation between halo and matter is B1 times the correlation function of the matter. It's a biased version of the correlation function of the matter. It has the same shape as the correlation function of the matter. If I did delta halo with delta halo, I would just get B squared with the power spectrum of the matter. And so the power spectrum, the clustering of halos, should have the same shape as the clustering of the matter and a different amplitude, because the high mass halos should have a higher bias factor. And so that's why on the first or second day, we made plots of weak lensing or galaxy clusters or galaxy clustering, and we plotted that. And I said, we can move around the amplitude of this signal, and we just ask, make them overlap, and we'll get a shape that we can compare with the shape of the CDM power spectrum. This is why. This is saying whatever biased tracer you take, you are going to change the amplitude of the clustering, but not the shape of the clustering. Yeah? It's a pretty non-trivial statement. Now, it's not obvious at the start.
The bias will depend on the mass of the
The bias depends only on the mass. Now, so this analysis was true on very large scales, because then I could truncate the Taylor series. Okay? But if I keep all the terms, and we have the full expression, so the only reason we're really doing the Taylor expansion is because the rest of the field concentrates on very large scales. But this you can do to smaller scales. And then you could have a Taylor series, but it's a strange thing when you have the full expression.
So you are saying matter is the baryonic matter?
Sorry?
You are saying power spectrum of matter, that is baryonic?
No, full dark matter. Full dark matter. Though they're not very different. On small scales they will be different, but on large scales the baryons are tracing the dark matter, and so. Yeah. It also means that if I want to do BAO, you might have worried, no, does it matter if I do BAO with dark matter or with galaxy clusters or with red galaxies or with blue galaxies? Does it matter? And this is saying that it matters because the amplitude of the clustering is going to be different. But for BAO, we don't care about the amplitude. We care about the scale at which there is the bump. And because this doesn't change the shape, the local maximum will remain the local maximum. And that's why you can do BAO for whatever tracer you want. Lyman alpha forest, galaxies, clusters, H1, doesn't matter. Yeah? And so it's a nice way to see why. Yeah? Okay. And now we are close to lunch. So this is a technical slide. Okay. If the others weren't technical, I don't know. Yeah.
We take perturbation in dark energy.
Yes.
Then on large scale also we can get the scale dependence of bias or not.
Okay, so there's two separate questions, right? So, because so far I haven't done scale dependence of bias, so that's what I'm about to do, okay? And then the second is, so that means, will I get bias to be scale dependent even when there's no dark energy fluctuations? I'm going to show you that's true. And then the next question is, so if you have fluctuations in dark energy, do you get some additional effect? which is also true. Okay? So I'm going to do the first one first, where we're still doing vanilla lambda CDM, no complications from that, and see what happens. Okay? So there are two things that are going to happen. As you go to smaller scales, you maybe have to go to next order. Okay? And maybe you can go to next order and truncate, but once you go to small enough scales, you should not truncate. But let's say you went to just a little smaller, so you're truncating, it's still okay. What's going to happen? You're going to have something with delta 0 squared. Delta 0 squared is something squared in real space, so it's a convolution in K space. If it's a convolution in K space, you're going to change the shape. And so you will get what looks like K dependence of bias in K space because of this convolution. So something that's actually simple in real space will appear to be K dependent in K space because of this convolution. Okay?
So it's actually the delta terms picking up the K factor.
That's right. It's actually just that you squared it in real space.
The of the delta square will be a K dependent quantity because of that.
That's right, because of the convolution. Okay? So some people call that K dependent bias. I'm going to ask an even simpler question. Can I get K dependence of bias or some scale dependence even without a convolution? So is it possible that this number is scale dependent? Okay? And so I'm going to show you where it comes from.
This bias factor is for over-dense region. What about the under-dense region?
Oh, no. So this power spectrum is for all regions. Yeah? It's all matter. Yeah? But so where the bias is coming from is it's saying that if I do something like this, because I only sat on halos, I only sat on some dense regions, and so I sat on a strange subset and I'm correlating with everything else. And so I'm getting some bias compared to this answer. Okay. All right. So that means you sit on some strange regions. So now let's go back and we'll ask, we'll write this as slightly more general. Okay. So before we said, to figure out what a halo is, we said that delta should be delta C. The slope of delta should be positive. But you know, there can be many other things that we haven't thought of. Okay? So let me imagine that there's the joint Gaussian distribution of all the things that could matter. Okay? So here I put shear because people are interested in that at the moment. Okay? So think of it as in that 3 by 3 matrix of second derivatives. I could just say, you know, there's that 3 by 3 matrix, each element of that, so 6 different elements. There are 6 numbers here. Okay, so those 6 numbers sitting here, and then I could ask for the derivatives also, so 12 numbers sitting here. Okay, so there could be whatever sitting up here. And then we'll say a halo corresponds to some rule about what those numbers should be. We've done the simplest. We took the trace of the matrix and we said it should have some delta C. But maybe there's something much more complicated which would be more realistic. Okay, so I'm just saying generally it will be like that. And then for that thing, then we could make the conditional one by saying, you know, that if I want the conditional, then I have to put all those things conditioned on the large scale density, the large scale shear, the large scale whatever. Okay. So it'll just be, again, some big, long Gaussian thing, but something you can write out. Okay, and so we can do a couple of things now. Okay, we can use Bayes' theorem. Okay, so of course we can expand in a Taylor series. Okay, and if we expand in a Taylor series, so that's the kind of thing we were doing before. Then you have to ask, you know, does this guy correlate with the constraint? Does this guy correlate with the constraint? Does all of these, each one of these, if they correlate with the constraint, they will bring a bias factor when you do the expansion. Now, delta prime, or suppose, you know, I have here 2 delta with 2 derivatives. If I have delta with 2 derivatives, that means it has 2 powers of k compared to this guy. So if I have 2 powers of k compared to this guy, then, and that's the only difference, in Fourier spaces, the derivatives are just the k squareds, okay? Then that means the correlation between this term and delta and 2 derivatives and delta will just have an extra power of k squared. And so I will get bias with k squared. I will get constant number from here and something that is proportional to k squared from here, which is pretty physical, but another way to think of this, another measurement way to think of this, is to say, I have this conditional distribution. Let me use Bayes' rule, so I write it as the full joint. Okay. The full joint, now I can write the other way around. I can write what is delta given all these variables. Okay. But if I want to calculate delta given all these variables, and I integrate over all values of delta now, that's asking for the mean value of the large scale density given all the things that make a halo. That means I'm calculating the halo profile, right? So in the picture, oh, I shouldn't have erased. You asked me to draw this nice picture, right? Which was, if I have a halo, there are many ways that I could have reached. There will be a mean way of reaching. This is what we mean by the halo profile. There's scatter around the halo profile. These are things that weak lensing experiments will be measuring, and we can calculate them. Yeah? Sorry? Basically like likelihoods. Yeah? Yeah, there will be. Yeah, so this thing gives you these kinds of priors and stuff like that. Yeah? And so that means the mean profile around a halo is something you can calculate. That's something that lensing is going to be measuring. And so we can start really going with data with this kind of thing. Okay. I think I should stop here. I want to hear just some pictures of the kinds of scale dependence that you get, right? The typical profile around a low mass halo, the typical profile around a high mass halo. They can have many different shapes, but all these things are things that you can calculate. A high mass halo should have a bigger radius, so I've divided by the radius, the size, to show you that this is important for later. The low mass halos have steeper profiles than the high mass halos. Some of you will know that NFW profiles have concentration mass relation. The low mass halos have steeper concentration, have bigger concentrations because they are steeper. The high mass are shallower. It's built into the initial conditions. If I want to measure voids, if I want to do all this for underdense regions, you effectively just flip the sign. And so now the small voids will have overdense regions around them. They will have walls around them. The big voids will not have as obvious walls around them. This is also seen in data. And so all this stuff you can calculate and quantify, and it's very close to the data, to the observations. And it's all coming from conditional Gaussian statistics with this one mapping, that spherical collapse mapping, to translate back to to translate between the evolved field and the initial field. And that's it. Okay, so I should stop there. We should have lunch. Yep. And we're set for halo model. Okay.